Okay, so you spent some time exploring this and looking for patterns in these tables. So the first thing that hopefully you notice right away is that we seem to have a pattern of dividing by 2, dividing by 2, dividing by 2. And the cool thing about math is that patterns always hold true. Whatever starts to happen, if you see a pattern developing, that pattern will continue. So if you had to make a prediction about what the next box would be, you've got to think, oh, I probably divide by 2. Well, when I do 2 divided by 2, I get 1. Okay, so that's really interesting to notice that 2 to the 0, 2 to the exponent of 0 is 1. And a lot of people think 0, but look at the pattern that's developing. Now, if we were to continue this pattern on, 1 divided by 2. So 1 divided by 2 is 0.5. Often in math, we don't want decimals. We want to be able to work with the fractions. So 1 divided by 2 is 0.5. Another way to say 0.5 is 1/2. Well, if I divide a half by 2, what's half of a half? Well, that's a quarter. And then what would half of a quarter be? So now think about a cake or something that's split into 4 pieces. Well, what if you split it again and you halved it again? You would end up with 1/8. The really cool thing that you might notice is, hey, look, we had an 8 here and we have a 1/8 here. We had a 4 here and we have a 1/4 here. We had a 2 here and we have a 1/2 here. That's kind of cool. And when we actually, the name for that in math, 8 compared to 1/8, they're called reciprocals. And reciprocal is a fancy, whoops, didn't come out right, but that's okay. It's a fancy word for flipping the fraction. So whatever was the numerator becomes the denominator, and whatever was the denominator becomes the numerator. And remember, the number 8 really just means 8/1. So really interesting pattern that we see developing. So now it's asking you to fill in some of the other boxes. So again, just a quick review, exponential form means writing it as a power, a base to the exponent of something. Repeated multiplication is just how many times does that base repeat? And then standard form is just a really fancy word for what would it equal? What's the answer? So 2 to the 3 is just 2 times 2 times 2. 2 to the 2 is just 2 times 2. That 2 repeats 2 times. 2 to the 1 just repeats 1 time. We're going to not do that box. Now, how do you think we would write 2 to the -1? Well, remember, 2 to the -1, we've just discovered by the use of a pattern that it's actually 1/2. So if this is 2, this one will just be 1/2. What do you think about 1/4? So again, think about, how do we write 4? Well, 4 was just 2 times 2, so this will be 1/2 times 2. And then how do we write 8? Well, that's just 1/2 times 2 times 2. Now we're going to stop for a second, and I want you to just look at this table and think about anything that might have surprised you. So again, you might be surprised that 2 to the 0, 2 to the exponent of 0, isn't 0, but it's 1. And the reason why it's 1 is this pattern. We divide by 2, divide by 2, divide by 2. We're never going to get 0 when we do that. The other thing you might be surprised by is you might have thought, like, 2 to the -1, you might have thought that that would be -2. Or 2 to the -2, you might have thought that that would be -4. But look at the base. The base is 2. So think about, is there any way that you can have a positive base that repeats that would end up being negative? And the answer is no, that's not possible. And again, we have to look at the power of patterns here. So let's look at another example. So here is the same thing, but with 3s. So again, what's happening? 81, 27, 9, 3. Now the last slide we divided by 2, but when I divide by 2, that doesn't work here. So what are we actually doing here? We're dividing by 3. Why 3? Well, the base is 3, right? So that makes sense. Well, if we kept that pattern going, what's 3 divided by 3? It's 1. So again, look, 3 to the 0 isn't 0, it's 1. Now, what if we divide by 3 again? We're going to get 1/3, not -3. What if we keep dividing by 3? Well, look at what happened above here, right? The next thing was 9. So what do you think this one will be? It'll be 1 over 9. But then if I divided that by 3 again, look at it, 1 over 27. Once again, I see this reciprocal relationship. 3 to the positive 3 was 27. 3 to the negative 3 is 1 over 27. 3 to the positive 2 was 9. 3 to the negative 2 is 1 over 9, and so on. As a repeated multiplication, again, 3 to the 3 is just 3 3's repeated. 3 to the 2, 3. Now, again, this is tricky. 3 to the negative 1, remember, I just write that as 1 over 3. 3 to the negative 2 becomes 1 over 3 times 3. And finally, 1 over 3 times 3 times 3. Again, it's just the reciprocal of the one above it. They're just reciprocals of one another. Again, 3 to the 0 was not 0, it was 1. And these negative exponents, we're not getting negative answers. Let's look at this final one. Same thing. What pattern do you see happening? So hopefully you see that, hey, we're dividing by 5 here. And again, why is it 5? Because the base is 5. So what's 5 divided by 5? That's going to be 1. Well, then what if I took that 1 and divided it by 5? Again, we're not thinking decimals, we're thinking fractions. I'm going to get 1 over 5. What do you think the next one's going to be? Again, keeping in mind of the reciprocal relationship we see above, it's going to be 1 over 25. And then the last one will be 1 over 125. These patterns are super cool, super powerful, and they let us do some really amazing things, in this case with exponents. So 5 to the 3 is just 5 times 5 times 5. 5 to the 2 is just 2 5s. 5 to the 1 is just 1 5. Now 5 to the negative 1, again, how do we do that? We just need to have the 1 over in there. We have to make it a fraction. 5 to the negative 2 and 5 to the negative 3. So here we've done a little bit of exploring with positive powers and some of the reminders of terminology. And we've done a little bit of exploring with what do we do with 0 as an exponent. And we've done a little exploring with negative exponents, which is kind of cool.